Okay, elementary statistics, looking at Chapter 10, Correlation and Regression. So we skipped over Chapter 9. We're going to move on to Chapter 10. We will come back into Chapter 9 where we talk about going back and doing paired tests and two values. In this chapter, we start looking at correlation. So one of the chapter problems we start talking about is, does a shoe size give some correlation to what somebody's height would be? So we start comparing comparisons of two variables, and is there some sort of connection between the two? So as we start off here, we start looking at a linear correlation coefficient, R, which is the number that measures how well paired sample data fit a straight line pattern on a graph. Okay. Basically, we talk about this as being paired data, sometimes called bivariate data. So as we start going through a couple definitions, we talk about correlation. So correlation exists between two variables that when the value of one variable are somehow associated with the value of the other variable, and then a linear correlation exists between two variables when there is a correlation and the plotted points of the paired data result in a pattern that can be appropriated by a straight line. So what we start looking at is we start looking at scatter plots. Let's come over to the next page here. We start seeing that we have different styles of scatter plots as we start looking at them. One of the things to reference in here is they should have some sort of pattern that is going to generalize, in this case, a linear line as we're going along. So we see overall that as we're looking at this, we see this kind of overall pattern going up. Let's say positive correlation. Here we have a negative correlation. As we see, the closer we get R equal to 1, or R equals negative 1, so negative correlation, downward correlation, negative R value, positive R value is a positive correlation. Do reference that as it's closer to 1 or negative 1, the more perfect of a line it is. So we see here we're kind of spread out a little bit more. Here we're a little bit more set defined. Once again, closer to that negative 1. If we come down here, we see no correlation. We can't tell if this is going up, down, flat. We have no clue what's going on here. And then here we see an R value is approximately 0. So we're kind of in between positive and negative. One of the things to recognize on here is this is not following any sort of linear line. It's actually following a quadratic line is what it's looking like. So it's not fit for this test. So definitions, we look at the linear correlation coefficient R measures the strength of the linear correlation between the paired quantity X and the Y values of a sample. Okay. Here they talk about this as a Pearson product moment correlation coefficient. Is what it's kind of referenced to in this book, once again because of the author. So there's a whole bunch of information here in this table. They have all this stuff here. I'm not going to go through everything in detail. And then they give us this nice formula for R. Boy, isn't that a nice way to figure out what's going on here. We're going to take the number of samples times the summation of X times Y minus the summation of X times the summation of Y all over the square root. This is horrible to calculate out. Horrible. A little bit more simplified version over here. R equals the summation of Z sub X, Z sub Y, the product in there, divided by N minus 1, where Z sub X denotes the Z-score for an individual. So we start relating each part into our Z values. Do realize that we have a calculator mode for this test. So we're not going to be doing anything by hand. The main thing here is we're going to be entering in our data. So we're going to have to enter in a list 1, a list 2, in which then we'll have to enter into a spreadsheet. And then we'll be able to go over to a calculator and talk about a linear regression t-test. Okay, so this is our key value right here. And then we'll enter in there. Notice that we will have to be doing a hypothesis test on this. Okay, so as we consider that hypothesis test, we have to reference what's going on. note that here. So that hypothesis test has a couple things that we need to know about it. We talk about the value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. So r squared is important because it describes the proportion of the variation in y that is explained by a linear relationship. So common errors involving correlation. Common error is to assume that correlation implies causation. So even though if we could see that something, oh, it's working here, this is looking good, it does not mean that it's actually working. Once again, a lurking variable is one of the effects that has this. Another error arises with the data based on averages. Averages suppress individual variation. And then a third error involves a property of linearity. If there is no correlation, there might be some correlation that is not linear, and a scatter plot depicts kind of some of this, so do be careful on this. So now when we look at our hypothesis testing towards this, okay, so in the hypothesis test we will have a null hypothesis and an alternative hypothesis. If I kind of zoom in here, the null hypothesis talks about rho equals 0. And in our alternative hypothesis, rho does not equal 0. So once again, this is a Greek letter that is presented here for linear correlation. Basically, the null hypothesis says there is no linear correlation. The alternative hypothesis says that there is linear correlation. Basically, why we do this is because, once again, if the alternative hypothesis is linear correlation, that means we can support that we have linear correlation. Versus that there's not enough evidence to reject that there is no linear correlation. So we're just kind of going within here. There's critical values. Once again, table A6 has our critical values for R. We'll talk about correlation itself. Overall, if we reject the null, we'll conclude that there is sufficient evidence to support the claim of linear correlation. If we fail to reject the null hypothesis, we'll conclude that there is not sufficient evidence to support the claim. So once again, we're testing towards linear correlation on this section. So as we kind of continue along, here they kind of give a method for a p-value. P-value method for hypothesis testing linear correlation. Once again, we have our values here. We have our t-test in this case, where we talk about r value, so we'll need to know our r value within here. Notice degrees of freedom changes a little bit, so we're allowing for 2 of these to vary within, so n minus 2 degrees of freedom. And then once again we got our correlations towards our statements of the null and alternative hypothesis. They have a couple other formulas in here. If you see over here, they got formula 1, formula 2 on how it works. Once again, going back within here. Do realize that this table right here is a nice table to note and have in here. The claim of negative correlation talks about the alternative being less than 0. Claim of positive correlation talks about the claim greater than 0. So if we want to define our hypothesis test a little bit more and not just worry about a linear correlation, if we want to know if it's a positive or negative linear correlation, this is how we would adjust that test for, once again, that p-value that we'd be working with.